Two uniform rods AB and BC, both of lengths 2a but of weight W and 3W respectively, are freely jointed at B. They stand in a vertical plane on rough horizontal ground. Both rods make an angle theta with the ground. The coefficient of friction between the rods and the ground is mu. Find the forces on the rods in terms of W and mu. Okay, rod AB has weight W. Now it's a uniform rod, so we can treat it as if all its mass is concentrated at its center of gravity. Okay, for a uniform rod, the center of gravity is at the midpoint of the rod. The total length of the rod is 2a, so the distance from A to the midpoint is A. Now, the weight of the second rod is 3 times greater, is 3W. Again, we put its center of gravity at the midpoint of it because it's uniform. Now, what about the forces at point A? Well, A is in contact with the ground, so the ground pushes up on this end of the rod. Let's call this force R. Now, if the ground was smooth, this would be the only force on the rod at point A, force pointing vertically up, and the rod would slip outwards because this rod is freely jointed to the second rod at B. So this angle is free to increase. So if the ground was smooth, the two rods would just collapse to the ground. So anyway, the ground is rough, so R is not the only force acting on the end of the rod. R is our contact force perpendicular to the surface of contact of the rod and the ground. So the ground is rough, so the rod pushes on the ground in this direction. Okay, so that will only happen if the ground is rough. If the ground is smooth, the rod would not be able to push on the ground in this direction. This vector would be 0. Now, by Newton's third law, since the rod pushes on the ground in the horizontal direction, the ground pushes back on the rod with an equal but opposite force. Let's call this force F. Okay, this all happens because the rod digs into the ground to some extent. The rod pushes on the ground, and the ground, by Newton's third law, pushes back on the rod. We have a similar situation over here. We have a contact force between the ground and the rod. So we have a force on the rod due to the ground, which is vertically up. That's perpendicular to the surface of contact. Now this force will have a different magnitude from R. Intuitively, we might expect that this force has a greater magnitude than R, because this rod has 3 times the weight of this rod over here. And we will see that that's the case. So let's call this force S. Now again, for the same reasons as before, we have a force in this direction at C. Let's call this force G. Now, what about the forces on each rod at point B? Well, let's look at a force on this rod due to the second rod. Let's suppose that it's in this direction here. Okay, so that's the force on the first rod due to the second rod. But by Newton's third law, we have an equal but opposite force on the second rod due to the first rod. When we sum these forces, we get 0. So when we're looking at the system as a whole, we can ignore these forces. They just sum to 0. They tell us nothing. Now, the system is in equilibrium, so the resultant force on it is 0. Okay, so that means that the sum of the magnitudes of the forces pointing vertically upwards is equal to the sum of the magnitudes of the forces pointing vertically down. So R plus S point vertically up must equal W plus 3W, which is 4W. Now we have forces in the horizontal direction. We can see that vector F must have the same magnitude as vector G. There are no other horizontal forces acting on this system. As I said earlier, the two forces acting here, the force on the first rod due to the second rod and the force on the second rod due to the first rod, are equal but opposite, so they sum to 0. Now, we can actually find vector S in terms of W and mu. Well, actually, we can find vector S just in terms of W by taking moments about the point A. So we are using our second equilibrium condition, which states that the sum of the moments about any point, in particular the point A, is 0. Now you can see that this is a very convenient point. The moment of R and F about the point A are 0, because A is on the line of action of both of these forces. The moment of G about A is also 0 because A lies on the line of action of G. The line of action of G is along the ground. So we only have to consider the moment of these three forces. These three forces have non-zero moment. Okay, so the sum of the moments about A is 0, and we saw in a previous video that that means that the magnitude of the sum of the clockwise moments about A is equal to the magnitude of the sum of the anti-clockwise moments. So to sum that up, I'll just say clockwise equals anti-clockwise. Okay, so what are the clockwise moments about point A? Well, we can see that W and 3W have clockwise moments about the point A. They act to turn the system clockwise about the point A. So let's get the magnitude of these clockwise moments and sum them. So we need to multiply W by the perpendicular distance of A to the line of action of W, this distance here. How do we find this distance? Well, we're in a right angled triangle. The hypotenuse of it is A. So if we multiply A by cos theta, we get the required distance. We multiply W by A cos theta. We do the same for the 3W force. What's the distance of the line of action of the 3W force to the point A? Well, if we do this construction here, we can see that the distance to here is A cos theta plus A cos theta plus A cos theta, or 3A cos theta. So we get 3W times 3A cos theta. So that's 9W A cos theta. Okay, so the sum of the magnitudes of the clockwise moments is equal to the sum of the magnitudes of the anti-clockwise moments, if we want the sum of the moments about our point A to be 0. So S is the only force that has an anti-clockwise moment about the point A. So we want the distance of A to the line of action of S. Well, that's just this distance here. So it was 3A cos theta from here to here, so we add on another A cos theta. So this distance is 4A cos theta. Now what is very convenient here is that cos theta cancels out and A cancels out. So we were lucky that the two trigonometric functions are the same. They both happen to be cos theta. So we can get rid of theta. Okay, so we have 4S equals 10W. So S equals 10 quarters W, which is 2.5W. Now we can go back up here to this equilibrium condition to find vector R in terms of W. So R is 4W minus S, it's minus 2.5W, which is 1.5W. So as expected, we can see that the magnitude of vector R, 1.5W, is less than the magnitude of vector S, which is 2.5W. That's because this second rod has 3 times the weight of the first rod. So the contact force of the rod on the ground is greater than the contact force of this rod on the ground. That kind of makes sense. And then by Newton's third law, of course, if the rod exerts this force on the ground, then the ground exerts an equal but opposite force on the rod, S. Now, we don't have enough information yet to find the forces F and G, the forces on the ends of the rod. So let's consider each rod separately. So this is the first rod. Now we don't know the direction of the force on B for the first rod. Could be like this. Could even be this way. It may even have a downwards vertical component. Like this, or like, we've no idea. So what we will do is draw in the horizontal and vertical components. Well, actually we can see straight away that the horizontal component of the force at B must be pointing to the left. The reason that it points to the left is that it must counterbalance force F. Remember, the resultant force on this rod must be 0. So actually we know the magnitude of this force. It's got to be the same as the magnitude of F. See, the other two forces are entirely vertical. They have no horizontal components. Okay, let's indicate the vertical component of the force on the rod at B. So this is a contact force, of course. As I said, it could be like this, or I'd assume that the vertical component is upwards, but it might not be. It might turn out to be downwards. We'll soon find out. So let's call this upward component y. So to get the force on this rod due to the second rod, we would just add these two vectors by the parallelogram law. We just complete a parallelogram, which is actually a rectangle in this case because we have the horizontal and vertical components. Now we found out what r is. It's 3/2 w, or 1.5 w. So for equilibrium, the sum of the magnitudes of the forces that point vertically up must equal the sum of the magnitudes of the forces that point vertically down. So there are two forces here pointing vertically up. So we have that 1.5 w plus y must equal the force that's pointing vertically down. It's the only force. If we solve this equation, we get y equals minus a half w. Now we get a funny result here, because y is meant to be the magnitude of this force. We get a negative answer. That makes no sense. The magnitude is always positive. So this contradictory answer, a negative value for a magnitude, means that this vector is pointing in the wrong direction. So the problem will only make sense if this force is pointing vertically down. See, now if we add a half w onto 1w, we get 1.5 w, and that is indeed equal to this upward force. So it checks out. So the forces pointing up are equal to the forces pointing down. So if we knew what F was, we could get the force on the rod at B due to the second rod. We could get this contact force. We could sum these two vectors, so we'd see it's pointing in this direction. Now we can go to our second rod. So we have the force on the first rod due to the second rod, this contact force here. So by Newton's third law, we have to have an equal but opposite force on this end of the rod. So what I'll do is I'll just copy this. So I've just copied part of this vector over here. So all I have to do now is just extend it. It's got to have the same magnitude as vector f, but it points in the opposite direction. Sorry, f, it's not vector f. F is the horizontal component of this vector. Well, the horizontal component of this vector has magnitude f, which is equal to g, by the way. So we can replace this with g, as we saw in the previous part. But now we see the upwards component must have magnitude half w. Okay, so we have just applied Newton's third law to get the contact forces between the two rods. Now we also have from the previous part that S is 2.5 W. So we found the forces in terms of W, except for F. We haven't been able to get F in terms of W. Well, you see, F is a force that varies from 0 to a maximum. F is the friction force, as we've seen in the previous video. Okay, it cannot exceed a certain maximum. So if the rod is on the verge of slipping, then F has reached its maximum value, and if the rod continues to slip, F will remain at that value. And we know from previous videos that that's given by mu times the normal force, which is 1.5 W. So this is the maximum friction force that can occur at point A. So this happens when the rod is on the verge of slipping. Okay, so that's this rod here, but what about this rod over here? What's the story here? Well, this vector has the same magnitude of this vector, so when vector F has its maximum magnitude, its limiting friction, well, this vector also has that value because it has the same magnitude, so we can write that in here. However, this rod will not slip. See, when this rod is on the verge of slipping, the maximum friction force is mu times 1.5 W, which would be the same here. But the rod is not going to slip. This rod will only slip when the maximum friction force is mu times 2.5 W. Because 2.5 W is the reaction here, which is greater than the reaction over here. So when this rod is on the verge of slipping, the maximum friction force will be acting. I'll try to indicate it here. I'll indicate it here in blue, and this maximum friction force will be have magnitude mu times 2.5 W. But you can see that that's not going to happen, because the friction force here is always equal to the friction force here for equilibrium. So the maximum value that the friction force can have here will be mu times 1.5 W. So this rod will not slip. Well, it might sort of slip eventually. Well, actually, it'll probably never slip. So the rods will collapse. This rod will slip out to the left. This rod will just collapse downwards. So slipping occurs when the maximum friction force is acting. So what's happening is that the rod is actually pushing on the ground in this direction. Okay, so the magnitude of this force will be the force on the ground due to the rod will be equal but opposite to the force on the ground, the force on the rod due to the ground. So this force will be at its maximum, and you know, for this particular normal force, the maximum is mu times 2.5 W, a force that is always greater than this force here. So as a reminder, the question was to find the forces on the rods in terms of W and mu. We can do that now when the system is on the verge of slipping. Well, the rod on the left is the only one that will slip. So F will equal mu times 1.5 W, which means that the horizontal component of this force here, this contact force on the first rod due to the second rod, is also mu times 1.5 W. Okay, this component is equal to this component here. And we have to have a similar situation over here. Okay, because this force here has the same magnitude as this force, which in turn has the same magnitude as the horizontal component of this contact force. So you see, we can't actually get this force directly. We have to take the vector sum of this force with this force. Okay, we won't do that. We'll just show the components of each of these contact forces. If mu equals 0.5, show that slipping occurs when tan theta is 4/3. Okay, so let's plug 0.5 in for mu. So this is the rod that will be the first to slip. So we'll analyze the forces on this rod. So this becomes 3/4 W. Okay, to find theta, let's take moments about some point. Now, we could use A or B, because either of those 2 points will simplify the problem. So let's use A. So by using A, we eliminate the moments of these two forces, because the line of action of these two forces contains the point A. So the moment of these two forces about A is 0. Alright, so we know that the sum of the clockwise moments about point A is equal to the sum of the anti-clockwise moments about point A in magnitude. So let's look at the clockwise moments about point A. We have W and a half W. They act to turn the bar or the rod clockwise about point A. So the distance from here to here is A, so we multiply A by cos theta to get this distance here, the distance of the line of action of W to the point A. So this distance is A cos theta. And similarly over here, we multiply a half W by not A cos theta this time, but 2A cos theta to get this distance. Now the 3/4 W force has an anti-clockwise moment about the point A. Notice, by the way, that we cannot get the moment of the contact force about the point A directly, because we haven't actually worked it out. We can only look at its components. We are actually using a result from the principle of moments here, which states that the sum of the moments of two forces is equal to the moment of the sum of the two forces. So we're getting the sum of the moments of the half W force and the 3/4 W force about the point A, and by the principle of moments, that's equal to the moment of the sum of those two forces, which is this force here, about the point A. Okay, so we multiply the magnitude of it, which is 3/4 W, by the perpendicular distance of the line of action of the 3/4 W force from the point A. So we want the distance from A to this point here. Okay, this is a point on the line of action of 3/4 W, so we want this perpendicular distance. Well, that's just the hypotenuse, 2a times the sine of theta. It's just the same as this distance here. We can see that W disappears out of this equation. A also disappears out of this equation. So we get 2 cos theta on the left hand side equals 3/2 sine theta. Dividing across by 2, we get cos theta equals 3/4 sine theta. So how do we get the result? We want tan theta in our result. So if we just divide both sides of this by cos theta, we will have sine theta over cos theta, which is tan theta. And finally, we just divide both sides by 4/3, so we get tan theta equals 4/3. This is what we have to show. So this gives us the angle when the left rod is on the verge of slipping. So here is the picture of the system when it is about to slip. This is the lighter rod, so intuitively we would expect this to be the first to slip out. Here's the friction force on the heavier rod, and this value is less than the maximum friction force, which is actually mu times 2.5 W, with mu equal to 1/2. So we have 1/2 of 2.5. It's 1.75. So the maximum friction force here would be 1.75 W. Or sorry, 1.25 W, which is 5/4 W.